ago I showed you a little clip of this video which I took from Derek over at Veritasium. Awesome channel, great video. He's bobbing these two balls up and down in the water. They're creating circular waves, but those circular waves are interfering to create these lines of constructive and destructive interference. It's pretty easy to see on water. Setting it up with light is a little bit harder. You need something called sustained interference. You need the interference to happen over a long period of time so that you have the opportunity to observe it. You also need a setup that's generally rather smaller than this because, again, light has a very tiny wavelength. To create this sustained interference, you need waves that are coherent and in phase. That means that they're the same wavelength and they're doing the same thing at the same time. You have waves that are doing this, they're coherent. In 1800, Thomas Young used pinholes and colored glass in order to get light of the same wavelength that was also coherent. In modern day, we just use lasers. They're cheap and they're easy to use. Instead of having two balls bobbing up and down on water, we can do this same thing by sending coherent light through a pair of slits. And you get a diffraction pattern on the wall opposite on the screen that is a series of bright and dark lines, and it happens for exactly the same reason that it does with water. Suppose you have two waves coming out of slits. My hands will be the slits, these are your waves, all right? When the two waves hit the screen, if they are a certain distance, if they're exactly the same distance apart, when these waves come off, you have troughs meeting troughs, and crests meeting crests, and troughs meeting troughs, and crests meeting crests. You get constructive interference everywhere in the middle in between. But off to the side a little bit, you get a crest meeting a trough, and then you end up with a trough meeting a crest, and then a crest meeting a trough, and a trough meeting a crest. You get destructive interference there, same thing on the other side. Go out a little further when you're a full wavelength different. Now again, you're getting crests meeting crests and troughs meeting troughs as the waves come out. And so what you have is the path length difference, the distance from your two slits to the screen. Here to here, the path length difference is 0. But if the difference from here to here and here to here is 1/2 of a wavelength, then you're going to get destructive interference. If the difference from here to here and here to here is off by 1 wavelength, you're going to get constructive interference. And so there's this very simple equation on the AP2 reference tables, which is this. It's saying that's your path length difference. It's an integer times the number of wavelengths, tells you how far apart they are. If your path length difference is a multiple of 1 wavelength, then including 0, then you will get constructive interference. If your path length difference is a multiple of 1/2, so it's half, 1.5, 2.5, 3.5, etc., you're going to get destructive interference and you're going to get a dark spot. And so you get these bright and dark lines. These lines are called nodal lines if they're dark and antinodal lines if they're bright, similar to the way we call the bigger spots on a standing wave antinodes and the points of destructive interference nodes. This experiment is proof that light is a wave, and Young used a little bit of trig. He found that the exact equation is d sine theta equals m lambda. That gives you the angle between these lines and the center line. We can also do an approximation of that using the fact that for small angles, tangent is very close to sine. You can get lambda equals dx over L. You can actually find the wavelength of light. So Thomas Young used this experiment to prove that light was a wave because it diffracts and it interferes, things that particles don't do. And then he also determined the wavelength of various colors of light. Something very similar happens when you have a light passing through a single slit, which we call single slit diffraction or Fraunhofer diffraction. What happens there is the path length difference between light refracting around the edge and light passing through the middle results in destructive and constructive interference. The math is very similar to Young's law. In fact, the equation looks identical. The major difference here is that this math actually gives you the location of the dark spots of destructive interference. With single slit diffraction, you get a wide, bright center spot and then dimmer, skinnier spots on either side. The higher orders are skinnier. Whereas with double slit diffraction, you end up with equally spaced, equally bright spots. So you can apply this equation, or the approximate equation, in order to find the so-called maxima, the bright spots, or minima, the dark spots, in either single slit or double slit situations. The double slit diffraction experiment is very, very interesting when we apply it to things like electrons, but that's a topic for another day.